So let's start the last session of the day. So our next speaker is Eduardo Miranda from the University of Campinas, and he will talk about emergent symmetry and transport in disordered quantum chains. Yes, I have to put this. Yes.
Tá ligado? Can you hear me? Okay. Really? Okay. So let me start by thanking the organizers, which, as you learned, are all old friends, for giving me this opportunity to speak here. I'm going to talk about emergent symmetry and transport in disordered quantum spin chains. Much of what I'm going to talk about has been covered by André, so maybe I'll try to go faster on those parts. This is work that I've been doing for the last couple of years with students, Victor Quito and Luis Faria, who is actually here somewhere, Pedro Lopes, and my good friend and collaborator, José Hoyos. The outline is this one here. I'm going to talk about disordered spin chains, and especially I'll rehash the SDRG method that you heard in the previous talks. But then I'll go on and talk about spin 1 chains, where I think we found new physics, which is this emergent SU3 symmetry. And I'll talk about generalization to other systems. And finally, at the end, I'll talk about transporting these systems. So the motivation here are some quasi-1D systems which are able to realize quantum spin chains, either with spin 1/2 or spin 1. And these systems, like this one here, as I will show you later, they don't seem to show any order down to very low temperatures. They have very anisotropic and quasi-1D. And for instance, the susceptibility as a function of temperature has this behavior, this sort of divergent behavior across many decades, which is reminiscent of the predictions of the theory I'm going to talk about, which is actually the dashed line over there. So I'm going to eventually come to this susceptibility here. There are also some interesting systems in cold atom physics which are proposed to realize disordered spin chains with arbitrary spin. So, this, as we learned in the talk by André, one-dimensional disordered quantum spin chains are one of the few systems in which we can analyze the role of disorder together with strong correlations, because these are spin systems, in a reliable and controlled manner. And so for that, okay, so I'm going to assume here, to describe the method, a disordered Heisenberg chain with random antiferromagnetic couplings, which are given by a distribution P of J, which can be taken to be fairly arbitrary initially, and I'll also assume that it has a high energy cutoff. So as André explained, the method, which was devised by Madas, Gupta, and Hu, is basically the following. You pick the largest coupling in your chain, and since you're interested in low energy physics, you look at the spectrum of the local spectrum of this bond. It's composed of a low energy singlet and a high energy triplet, and the triplet is separated by this very high energy scale from the low energy singlet, so you just throw it away. And but you not only do that, but you also calculate the effective coupling, the effective new coupling that appears between the neighboring spins S1 and S4, and this is given by second-order perturbation theory by that formula. And as André pointed out, you should note that the J prime, the renormalized J that appears, is smaller than both J1 and J3. It's wrong here. Okay, so there's a tendency to form new bonds with lower coupling constants. Okay, the net result, of course, after you eliminate and renormalize is that you have the same Heisenberg chain back again, but with new couplings different from the ones that you started with before. And then you iterate this many times. Okay, so pictorially you can look at this as the following. You have the chain, you find the strongest coupling, you eliminate it, renormalize the chain by generating new couplings. You do this progressively, and so on. And eventually you start decimating chains which appeared through the decimation procedure. So these are longer bonds now. You finally come to that low energy scale where this is the strongest one system. And when you decimate it, you start forming these large bonds, these strongly coupled pairs, coupled by very long bonds, which are weaker and weaker as you go down in energy. So this is what's called, so the ground state is going to have this structure that is pictured here. This is what's called a random singlet phase, sometimes called a valence bond glass. And the important thing to keep in mind is that there are going to be bonds between widely separated spins of all sizes. Now, it's interesting that if you analyze the flow of the coupling constant distribution, as André also mentioned, they are all attracted to a very singular distribution, like this one here, a power law with an exponent that's continuously decreasing as a function of the energy scale. And the important thing to notice about this fixed point distribution, or close to fixed point distribution, is that if you measure the effective disorder by the fluctuations in J compared to the mean, this is actually a diverging quantity as you lower the energy scale. Okay, so what that means is that the effective disorder of the renormalized chain becomes bigger and bigger, and actually grows without limit as you approach the ground state. So because the method was based on perturbation theory, and because the flow takes you to a situation where the distribution is very large, it means that the perturbation theory that you're doing becomes better and better as you go along. Therefore, the method becomes more reliable as you go along. And asymptotically at very low energies, the method becomes asymptotically exact. And that's what's, if all of these things happen, this is what makes you confident that you can make reliable predictions with this method. Okay? The ground state has this structure. Now the question is, what about the excitations? So the excitations are basically, can be viewed as broken bonds of these large spin pairs that I mentioned. So actually you can show that the energy, the coupling constant of the large bonds scales with as a stretched exponential of the size of the bond in this fashion, with this activated dynamical exponent psi, which is equal to 1/2. And so that at finite temperatures, all the bonds that are larger than this L0 are going to be broken into triplets. This L of t is obtained from this by inverting this relation, by putting E equals to T and then inverting this relation. So then you have this length scale above which all bonds have been broken. So at finite temperature, the structure of the system is given by this. You have a collection of singlet bonds and a collection of free spins. Okay, and of course, the average density of these free spins is given by the inverse of this L0, which, as you can take from here, grows like this 1/log to a certain power. So that allows you to now make physical predictions about the system. So for instance, the spin susceptibility of the system can be very accurately described by the following. If you apply magnetic field, the singlets are going to give no response, they're inert, but the free spins will give you a Curie-like response. So since there are 1/log to this power of free spins, this is the prediction of the theory for the susceptibility. Okay? And this is what the curve that I showed at the beginning, where it comes from. You can do the same thing for other physical quantities, but in this talk, I'm going to focus just on this particular one here. So the picture that I want you to keep in mind at this point is that at finite temperatures, you should view the system as a collection of singlets and free spins. Okay? Now, as I said, I'm going to now look at spin 1 chains. In the case of a spin 1 chain, besides the Heisenberg term, you can also have a biquadratic term. It's allowed for a spin higher than a half. And that makes the analysis now a little bit more complicated. Okay? So in principle, you have different coupling constants for these two terms, which I call Ji and Di. Now, it's very advantageous not to talk about J and D separately, but to choose sort of radial and angular variables from these two, such that if you look at this plane of J and D, now you can talk about the E coupling constant and the angle. Okay? This is going to be much more convenient for the discussion. And I'm going to concentrate here on random systems where the initial randomness is only in the radial direction, but the initial angular variable is constant throughout the lattice. Okay? The method can be generalized to situations where the theta angle also fluctuates, but you have to start the analysis with this simpler case. Okay? So, as before, the decimation procedure is quite simple. You look at a certain strongly bound pair. Now, because it's spin 1, you can have different level structures. For instance, you can have a singlet ground state and triplet and quintuplet excited states, or the ground state could be a triplet or a quintuplet. And now, if you put these three possibilities in this circle, you realize that in this region here, you form spin 2, right? The quintuplet. In this region, you form spin 1. And in this region, you form a spin singlet. Okay, this is just for the local problem. In this talk, I'm not going to talk about the region, the dashed region over there, because there, as you saw, there's a tendency to form large spins. And the phase that appears in that case is a phase that has been analyzed, but it's not the focus of my talk here. Okay, so I'm going to look, my phase diagram will be concentrated on this wedge of the circle here. So now I'm going to give you the result of the analysis of the SDRG. If anyone is interested in the details of the analysis, I can give you later in person, but here I'll be mostly interested in the results. So the result is the following. In this region, which I call 2 here, this yellow region, which contains the Heisenberg point, the phase is pretty much the same as in the spin a half case. Okay? If you look at this diagram, you see that most of that region you form singlets. So it's not too surprising that you should get the same physics. It's not exactly the same region. It's actually, you see this angle is arctangent of 1/3. This is pi over 4. So it's a little bit extended region, but the physics is the same. So the ground state is a random singlet phase. At finite temperatures, you liberate some of these bonds. You form free spins, and you have this susceptibility that I showed before. Okay, so that's not too exciting. However, in that region, which I call 1 over there, something more interesting happens. If you remember the previous circle, that's precisely inside the region where you form spin 1 as you decimate. Okay, so a process that happens in this region is the following: you decimate a pair, you form a new spin 1, which will later decimate a neighboring spin and then form a singlet. So the effective singlet that was formed here is now composed of 3 spins instead of 2. Okay, and you can actually show that there are actually spin singlets formed with 6 spins and 9 spins and so on. But the trios are the most abundant ones, so I'm going to talk about just the trio. So the structure of the ground state is a little bit modified now. Okay, it's a random singlet phase composed of random trios now. And the excitations now are also a little bit different, because you can show that the activated dynamical scaling I had before still survives, but with a different exponent, 1/3. And from this, you can get the susceptibility, which now has a different log correction to the Curie result. Okay? So now, as I said, you should look at the finite temperature state as a collection of random singlets and free spins. Okay? So that's the picture in that phase 1 over there. So so these are the details of the RG flow, which I can discuss if someone is interested. There are fixed points and stable and unstable fixed points, and you can actually, by basically a symmetry analysis, identify their locations, but I'm not going to enter those details, okay? So let me talk about emergent SU3 symmetry. So the first question is, what does SU3 have to do with spin 1? Okay, as you all know, spin 1 is a 3x3 representation of the group SU2, the covering group of rotations. So the question is, where does SU3 come in? And the answer is the following: if besides the 3 spin operators, spin 1 operators, you form these quadratic combinations of spin operators, which are usually called quadrupolar spin operators. The 8 operators that you form in this way will be the 8 generators of the SU3 group, of the fundamental representation, or sometimes called the quark representation of the SU3 group. So if you don't know anything about SU3, believe what I'm saying, you can build a representation, the fundamental representation of SU3 from these spin matrices here. So this is where SU3 comes in. Now, if you also change the sign of the 5 generators, the quadratic ones, you generate a different representation called the anti-fundamental or anti-quark representation of the same group. Okay? So the SU3 group, unlike SU2, has 2 representations of dimension 3, okay, the fundamental and the anti-fundamental. So now, the point is the following. You can take the Hamiltonian that I was analyzing before, you can rewrite it in this way, okay, where in terms of those generators of SU3. If you look at this guy here, it has all the 8 generators of SU3, but it's actually an isotropic SU3 because this coupling constant in principle is different from that one. So if you look at the circle now, there are particular points, the pi/4 minus pi/2, where this coupling is equal to that one. And these particular points have explicit exact SU3 symmetry, and this is well known for the clean case. The pi/4 point is called the Unimian-Lai-Sutherland point, and the other point is also well known to have this explicit SU3 symmetry. So in work done many years ago, Jose and I analyzed this exact SU3 or SUN symmetric chains. So that paper applies to these particular points. But what I want to talk about is the following: that even away from those points, so even within this full phase 1 or this full phase 2, at low energies, there is an emergent SU3 symmetry. And I'll try to explain why. And the reason is the following. As I said, you can look at the structure of the fixed points in both phases as these collections of singlets and free spins. And now you can show the following. Both these spin pairs and the spin trios, they are not only SU2 singlets, but they're also SU3 singlets. Okay? So if you imagine applying an SU3 magnetic field, they are also going to be inert. They're also going to show no response to this generalized magnetic field along the SU3 axis. In other words, if you couple to those 8 generators of SU3 with a magnetic field, these guys are singlets. Now, the other part of the phase, which are these free spins, they also, they form a 3x3 representation of SU3, which is either a quark representation or an anti-quark representation. So this also transform as a particular representation of SU3. Okay, and you can actually think of the trios as a bound state of 3 quarks. So we like to say that this is a baryon. and the singlet pair is a bound state of a quark and an anti-quark, just like a meson. Okay. So in the end, the conclusion is that the building blocks are both the free spins and the singlets are SU3 symmetric. So it should be no surprise that the response of the system also has the same symmetry. So, okay, so we like to call this phase a mesonic phase and the other one a baryonic phase, okay, with analogy to high-energy hadronic physics. So as I said, if you now apply magnetic field across the SU3 directions or along the SU3 directions, okay, and calculate a sort of generalized susceptibility, you're going to have the same behavior in the 8 directions, okay? So this is what we call an emergent SU3 symmetry, okay, which happens in the full phase 1 and also in the full phase 2, okay? So at this point, we were very happy with the result, but then the obvious question was, okay, so if you now put spin 3 halves, spin 2, are you going to have these higher symmetry groups there also? And we looked at it, and the answer, unfortunately, was no. Okay, so we did have conventional random singlet phases with pairs, which do have these enlarged symmetry, but these are random singlet phases, just like the Heisenberg point. And we did find also a phase with a different dynamical exponent, but it did not have the emergent symmetry. So we're a little bit frustrated in this attempt. But then my student, he suggested the following. Maybe the way to go is not what we did to increase the spin, but take a different route. So spin 1 is also the fundamental representation of SO3, which is a different group, right? There's this covering property that relates SO3 and SU2. They're almost isomorphic. Okay, so S1 can be viewed as the fundamental of a representation of SO3. So maybe the way to go is not SU2 with spin greater than 1, but SO3 to SON. Okay, so this is sort of a crazy idea, and it turns out that it works perfectly. Okay, so this is the way to generalize our result for spin 1 to other groups. So the SON Hamiltonian, I'm not going to give the gory mathematical details, but it can be written as an anisotropic SUN model, and you can have emergent SUN symmetry in these SON models. Okay, so the same mechanism applies. You do have a mesonic phase, which is this blue phase, a baryonic phase, which is this green phase with emergent symmetry and so on. But now you see that, for instance, for SU5, you're going to form singlets made out of 5 spins. Okay, so this can be done. The question is, is this relevant to any physical system, SON chains? Do they exist? So the nice thing about SON group is that it is isomorphic to other more common groups for low values of n. So for instance, SO2 is isomorphic to U1, and it can have an emergent SU2 symmetry, and that's nothing but the XXZ chain that was discussed, for instance, in Andre's talk. Okay, so as he showed, I don't know if you remember this, but the correlation function for the spins in the x direction and the z direction, they decay with the same exponent. This is an example, a hidden example of this enlargement of symmetry that is shown here. SO3 to SU3 is the spin 1 case that I was talking about. Now SO4 is more interesting because SO4 is isomorphic to SU2 cross SU2, which is just 2 spins a half. And this is the famous Kugel-Komsky model, where you have both orbital and spin degrees of freedom at the same time. So this model here has an SO4, a hidden, or perhaps not hidden, but has an SO4 symmetry. And with this order, you can actually, you can actually have an emergent SU4 symmetry in this particular model. SO5 is not, there's nothing interesting there, but SO6 is isomorphic to SU4. So you can have SU6 emerging out of SU4. And for SU4 or SO6, there are proposals with cold atom systems to realize these systems as genuine realistic systems, okay? So now, in the last few minutes, if I may, 5, I'm going to go quickly over the transport part. which is the following. So the SDRG procedure can be generalized to look at dynamical quantities, for instance, at the optical conductivity. This is the Kubo formula for the conductivity at finite frequency. And you can do the same procedure that I described before, but now you renormalize this tau here, which is just the current operator. In this case, it's a spin current operator for the spin chain. And you have also to renormalize the size of the, so for instance, this size here, if this is 1, 1, 1, this is 3, right? Because it's composed of 3 bonds. And once you do that, you can use the SDRG method to look at the optical conductivity. And the reason why we looked at this is because there was this claim in the literature that the XXZ chain, if you calculate the optical conductivity, it diverges at the low frequencies as a logarithm. In other words, it's a metal. And we found this very strange because the delta equal to 0 limit is a non-interacting fermion limit with hopping disorder, as we also heard before. And this is not a metal. This is an insulator. This is the state at the center of the band of the off-diagonal disorder case. And the states are localized for those. The state in the middle of the band is localized. It's anomalously localized. It's localized as the exponential of square root of x, but still localized. It shouldn't behave like a metal. So what's the problem? Well, the problem is the following. What people calculated was the average conductance. Okay, the average conductivity. And as we know from Vlad's talk, okay, the conductivity or the conductance in one dimension has huge fluctuations. And the average value is not a good tool to look at the conductance of the system. So it turns out that the typical value, which we are going to take as the geometric average of the conductance or the conductivity, is very different. Okay, and the previous result, the metallic result that was claimed, was obtained for the average conductivity. Okay, so we actually looked at the distribution of conductivities, and you see they're extremely broad distributions. So this is in the region where the average value is diverging, supposedly metallic. But you see, it's extremely broad. This is log scale. Okay, this is even broader. Okay, so now what you have to do is to look at the typical conductance, not the average conductance. So now this is the average conductance, appropriately rescaled by the size of the system. So for any size of the system, all the average conductivity curves fall into this universal curve. This is the metallic behavior. This is finite size effect. Okay, so for in the thermodynamic limit, you just have this part here. Okay, but as you see here, as you increase the system size, the typical value goes down to 0, and that's typical of an insulating system, not of a conducting system. So everything is fine, actually. Okay, the system is not conducting, it's not metallic, and it's actually an insulator. And this can be generalized to the spin 1 case that I talked about. The same physics applies there. While the average conductivity appropriately rescaled by the system size does not change, the typical conductivity goes down and down as you increase the system size. Okay, so let me just finish with the conclusion. So I showed you a generic path for emergent symmetry in disordered systems. Okay, disordered interacting systems, this SON to SUN route. And I also, when I talked about transport, but not only transport, but in general in these systems, you have to be very careful when you talk about physical quantities when they are very widely distributed. Okay, so with that note, I finish here. Thank you.
So we have time for a few questions.
How are the results sensitive to the type of disorder?
So, okay. So in the spin 1 case, there are other methods to analyze the system. Spin a half case. Let me start with the simpler one, spin a half case. It's known through numerics and also through perturbation theory around weak disorder that apparently any initial disorder will take you to the fixed point that I showed you there, okay? And whatever the disorder is, it goes there. And it's universal in the sense that at the end, at low energies, you flow to that case. For the spin one case, it's more complicated because for instance, the Heisenberg model is gapped. And the gap sort of protects the system from disorder, so disorder is irrelevant for weak disorder. But then for large enough disorder, this applies. Large compared to the gap, for instance. But you see, in the spin a half case, doesn't matter. Okay, so this is.
So, any other questions? Actually, I do have one. You just mentioned the Haldane gap of the spin one chain, and how it makes the system irrelevant to weak disorder, insensitive to weak disorder. But if you go away from the Heisenberg point, eventually you close the Haldane gap.
Yeah.
And would you be able to look at, yes. Would you be able to look at the closing of this gap, of the effect of disorder on how this gap is closed compared to the uniform limit?
That's a good question, but the method is not tailored for intermediate or weak disorder. It can be adapted to the intermediate disordered case. It has been done. Basically, what you do is instead of throwing away every excited state, to just throw the largest one, and then you're able to identify this so-called Griffiths phase close to the boundary where you go into the random singlet phase. So perhaps with that method you might be able to do that, but this requires a method that's more subtle, right? The SDRG philosophy is always strong. You assume strong disorder. Okay.
All right.
Apart from these funny exponents, is there any experimental consequence of these bigger symmetry groups being applicable?
if you could measure a log correction, a different exponent and a log correction.
No, but is there anything more direct than just measuring a number that a divergence? Is there any? I mean, if I have a Heisenberg chain, I can tell from an XY chain by putting it in a magnetometer, and
yeah, I mean, for instance, we had a look at
tensor quantity that I can measure that would reflect the symmetries.
Yeah, that would be one thing, but
off-diagonal, nonlinear, off-diagonal susceptibilities, or anything that would.
I don't know if you can measure that, but can you?
I could put the field in one direction and measure response in another. I mean, there's generalizations.
Yeah. Well, one thing that comes to my mind right now is the spin response, right? The Q-dependent, omega-dependent spin correlation function that you might be able to access with neutrons, for instance. There are predictions for spin a half case, and which could, in principle, be generalized to this phase, but we haven't really looked at it. But in principle, I think that would be the place where I would look at. Okay.
Any other questions? So let's thank the speaker again. Do you have an adapter? Yeah.